Welcome everyone to another, the fourth, I guess, last HDL seminar of the year. The final one, just a heads up, will be on June 29th before we take a break for 2 months to resume in September. So today I have the pleasure of introducing Andrew Koshyk, a former, I guess, lab member of, not mine, but Glenn's. We shared a lab space or whatever. Anyway, Andrew joined Brent's lab group in 2021 after he completed his undergraduate degree in mechanical engineering at McMaster University in Hamilton, Ontario. He is just about ready to defend his PhD, I think sometime at the end of this summer or a couple months from now. Masters. Oh, no. Okay. He's going to start a PhD with Brent after he defends his master's degree in the fall. Putting the cart before the horse. This is brilliant. Okay. Aside from that, the other thing you want to know about Andrew is he's unfortunately a Maple Leafs fan. Yes, but we let this go, and you've seen him probably around sporting some Flames gear, so he is becoming accustomed to I mean, there's a bit more hope in Calgary than there is in Toronto after we went down again for another year in a row. So Andrew has been studying subchondral fatigue of these equine horse bones. It's been super fascinating to learn a lot about horses, horse bones, just kind of generally everything. I mean, the structure, the microstructure of these bones is quite fascinating, and just simply how difficult it's been for him to get from taking a whole bone into testing this has been quite an interesting journey. So without further ado, I'll turn it over to him. And his title is Influence of Microarchitecture on Fatigue Behavior of Equine Subchondral Bone.
Thanks a lot, Michael. So yeah, we'll just get right into it. So musculoskeletal injuries are a really significant source of lost training time and morbidity amongst racehorses. And bone injuries account for the largest proportion of fatalities among these equine athletes, particularly at this fetlock joint, where we see fractures of the third metacarpal and the proximal phalanx bones accounting for the majority of these fatal bone injuries. So this fetlock joint is located here, sort of at the distal end of the equine forelimb. And then here's just a little bit, I guess, the anatomy of this joint. So it's composed of this third metacarpal or MC3 bone up here, and that's in contact with the proximal phalanx or P1 bone over here. And then we also have the two proximal sesamoid bones on the palmar aspect of this joint. So we see fractures occurring in both the third metacarpal and proximal phalanx bones, and those are sort of the injuries that I'm going to be focusing on today. So here are sort of some radiographs of these injuries. In the third metacarpal, these injuries often originate, or almost always originate, in either the medial or lateral condylar groove. When we see them originate on the lateral side, they typically propagate up and then exit through the lateral cortex over here. In the middle, we see an example of one that originated in the medial condylar groove. And those ones typically propagate up more axially, leading to more of a spiral fracture, often displaying more of this Y configuration. And then on the right here, we have an example of a P1 fracture. So these are some pretty nasty looking injuries, and they're also really difficult to treat and often don't have the best outcomes for these horses. So why does this joint seem to sustain so many injuries? So at this location, tendon wrapping generates really high cyclic loads at this joint. Some previous work has shown contact between the third metacarpal and P1 bones can experience up to 50 newtons per kilogram during a gallop. So you can imagine for like a 500 kilogram thoroughbred racehorse, that's over 25,000 newtons of force between these two bones, which is pretty significant. And then in this little clip here, you can kind of really see how much extension this joint really goes through at high speed running. These sesamoid bones in the back often come into contact with the ground, putting the joint at almost a 90-degree angle. So that causes a lot of these tendons running along the palmar aspect of this joint to generate really high loads, sort of driving those sesamoids into the third metacarpal and proximal phalanx. So these injuries initiate in the subchondral bone, refers to the bone underlying the calcified cartilage, and it's going to include both the subchondral cortical plate as well as some subchondral trabecular bone. And that's represented pretty nicely here in this figure, where we have our layer of calcified cartilage. Underneath that, we have a small area of a subchondral cortical plate, which then transitions into more subchondral trabecular bone. So one of the characteristic features of these injuries is they have a really consistent pathological morphology. They almost always originate at the same locations, propagate along similar fracture paths, and they always occur in horses that habitually race and train at high speeds. And they're commonly seen during these high periods of high speed racing and training, so during the racing season. So therefore, these injuries are believed to be a result of this high-speed racing and training, and there's a consensus that they're what we consider to be a mechanical fatigue phenomenon. So mechanical fatigue is just characterized by the accumulation of micro damage as a result of repetitive cyclic loading. So over time, if this loading is allowed to continue, we'll see a progressive degradation in material properties. And then as this micro damage continues to accumulate, and in the absence of adequate repair and remodeling, we'll eventually see fractures at loading magnitudes well below the ultimate strength of these materials. So there's been a little bit of previous work trying to quantify the mechanical fatigue behavior of the subchondral bone through some ex vivo mechanical testing. And like some other materials and other bone samples, we typically represent this using what we call a stress life plot, where we have our stress amplitude plotted on the vertical axis, and then our fatigue life, which we just define as the number of loading cycles a material can withstand before failure, plotted on the horizontal axis. So the relationship is typically pretty nicely represented with this inverse power law. But when we look a little bit closer at some of the underlying data, we see there's actually a pretty significant amount of scatter. And this happens even when samples appear identical in macrostructure and they're loaded to the same magnitude. You know, we see this scatter span 2 and even 3 orders of magnitude. So given that we see this scatter, even when we hold all these extrinsic loading parameters constant, it sort of leads us to believe that it's a result of the inherent variability in the bone microarchitecture. So if we look at some bone samples, so these are samples taken from 3 different human cadaveric femurs. So we can really see based on the sex of these donors and their age, how different the microstructure can really look between bone samples. And it's similar in some of our horse samples based on their age, their sex, their breed, and other factors like their training history, frequency and intensity. All these microstructures can look really different. So given how different they look, I think it's fair to expect these bones to all behave differently as well. But there hasn't really been much work looking in equine subchondral bone at how this variation in microarchitecture can influence fatigue life. But there has been a little bit of work looking at human and bovine bone. So a lot of this work has demonstrated that a large majority of this scatter can be attributed to differences in microarchitecture. And there have been a few studies that have found porosity to really strongly negatively correlate with the fatigue life of cortical bone. So in this plot here in the top left, we just focus on those filled in black dots, which is secondary bone. You see there was a pretty strong relationship between porosity and the number of cycles to failure. And then this porosity is largely going to be attributed to void space created by vascular canals in the cortical bone. So it's going to be a function of both the size of the canals as well as the number of canals present in the bone. So some subsequent work found that this porosity led to a decreased fatigue life, more so because of the size of the canals rather than the number of canals present. You can see the high correlation here with the size of the canals. And then some other work from our group developed these micro-CT based finite element models where we were able to quantify stress concentration volume. And we found this metric to be a much better predictor of fatigue life than either nominal stress or strain. And then looking at some work in equine subchondral bone specifically, again, it's been super limited. But there was one study that found fatigue life was positively associated with bone volume fraction in the proximal and middle regions of this subchondral bone sample. But really beyond this, there's been very little work trying to explore the mechanism behind these fetlock fractures. And really beyond our understanding of the importance of bone volume fraction, we're really lacking, I think, a more sort of mechanistic understanding of the relationship between bone quality and fatigue resistance. And that makes it really difficult and really limits our ability to try and predict fatigue failure in these horses. So as a result, our objective was to try and quantify the influence of microarchitecture on the mechanical fatigue of equine subchondral bone. So to do this, we first used some high resolution micro CT imaging to quantify the microarchitecture of our samples. We then quantified fatigue behavior through some ex vivo mechanical testing. And finally, we developed some micro CT based finite element models to quantify stress concentration volume. So into our sample preparation, we collected 12 forelimbs from 8 horses that were euthanized for reasons unrelated to this research. We had 5 females and 3 males with ages ranging from 2 all the way up to 25 years old. And then we cored out some cylindrical bone samples, much like the one you see on the right-hand side here. So we cut those out of the medial and lateral condyle of the third metacarpal towards the palmar aspect, as well as from the medial and lateral condyle of the proximal phalanx. We then removed the cartilage with a precision saw and then polished the samples to ensure the surfaces were plano parallel. Next, we used some high resolution micro CT imaging on our samples. We scanned with a voxel size of 6 microns and then segmented our images using MATLAB and quantified the microarchitectural parameters using Fiji. So a few of the things we looked at were bone volume fraction, tissue mineral density, and then pore diameter, spacing, and the number of pores. So here are sort of some example images that we get from our CT scans after they've been segmented. So like I mentioned before, this subchondral bone is going to include both a subchondral cortical plate as well as some subchondral trabecular bone. So up here, sort of a representative image of the cortical region, and then below that is what typically we would see more in the trabecular zone. Next, we did our mechanical testing. So we potted the trabecular end of each sample to a stainless steel plant with some bone cement. We cyclically loaded our samples in load control up to 70 megapascals of compression at a rate of 2 hertz while they were immersed in PBS. And then we quantified fatigue life using a stiffness criterion. And finally, we developed some micro CT based finite element models. So our elements from our micro CT images were coarsened to a voxel size of 24 microns and converted to linear hexahedral elements. And we did a mesh convergence to make sure it was sufficiently converged at this element size. We then assigned homogeneous linear elastic material properties, and a uniform compressive load was distributed over the entire subchondral surface with the trabecular surface nodes fixed. And then we defined stress concentration volume as the volume of material experiencing a stress greater than the yield strength of equine subchondral bone. So getting into some of the results, we found stress concentration volume was a much better predictor of fatigue life than normalized stress. And normalized stress, we divided our stress by the initial modulus. So it's not, we weren't directly measuring strain, but for all intents and purposes, this is a measure of strain. So we again see stress concentration volume at a much higher correlation. But I think we should note that this was when we pooled all our bone samples together from both the third metacarpal and from the proximal phalanx. So when we look at those bone samples individually, we start to see these relationships change a little bit. So if we just look at the top row of this table, we can see that normalized stress and stress concentration volume were almost equally predictive of fatigue life in the third metacarpal bone. But in the proximal phalanx, we see they're quite different in stress concentration volume. Was a noticeably better predictor of fatigue life for the proximal phalanx bone. So then we tried to investigate a little bit more why we were seeing these different relationships between the bones. So one thing we looked at was the degree of mineralization, the tissue mineral density. And we found there were some relationships, but it didn't explain a huge amount of the variability. So this sort of suggests that this difference isn't necessarily explained by the degree of mineralization in these samples, but can probably be attributed more so to differences in the microarchitecture. So the next thing we looked at was bone volume fraction. And we found this to be pretty strongly related to the fatigue life and stress concentration volume of both of our bone samples, which we thought was a nice finding, was what we expected. But one thing is, although bone volume fraction correlated really nicely for both bones, the bone volume fraction actually looks quite different for each one. So here we plotted the bone volume fraction as a function of the length of the sample, whereas 0 millimeters on the x-axis corresponds to the articular surface, and then 6 millimeters is deeper into the trabecular zone. And we found that third metacarpal, which is plotted in blue, had a pretty consistent bone volume fraction throughout the sample, whereas the P1 was a much more heterogeneous sample in terms of the bone volume fraction. So we dug into this bone volume fraction a little bit more and conducted this regional analysis where we split our bone samples up into a superficial, middle, and deep region. And we found stress concentration volume had the strongest correlation with bone volume fraction in the middle region. And that was particularly true for the P1 bone at a super high R-squared value. And then looking back at that plot of sort of bone volume fraction, we see this middle region, especially for the P1. That's where we saw a lot of that variation in bone volume fraction. So we're still working through some sort of more exploratory analyses with this, but so far we found sort of the later that it transitions into the trabecular bone, sort of reflecting a thicker cortical plate, that improved fatigue life. And we're still looking into that a little bit more. And then for some of the microstructural parameters, we found that stress concentration volume was largely attributed to pore size rather than the number of pores. So there really wasn't any relationship with the number of pores present in these samples, but we did see some nice correlations with the size of the pores present. So overall, I think identifying some of these microstructural features that are most relevant to the fatigue process can just help us clarify the underlying mechanisms of this fatigue process. And I think that's really important to understand before we move towards predicting these fractures. So we found that stress concentration volume was a better predictor of fatigue failure than normalized stress in the P1 bone. But we found they were pretty equally predictive of fatigue failure in the third metacarpal. And we think this can be attributed to the heterogeneity of those P1 samples in terms of their microarchitecture. So while the MC3 displayed a pretty consistent bone volume fraction throughout the sample, and pretty similar pore size throughout the sample. That's one reason why we might think normalized stress was representative, sort of the stressing throughout the entire sample, whereas the P1 was much more heterogeneous compared to the MC3. And then with our regional analysis, we found bone volume fraction in the middle region had the strongest correlation with stress concentration volume, particularly for the proximal phalanx bone. And we found tissue mineral density did not explain a huge amount of the variation. So probably the degree of mineralization alone isn't enough to look at, but rather the microarchitecture might be something we should be focusing on instead. And with the microarchitecture, we found stress concentration volume was largely driven by the size of the pores rather than the number of the pores. So I think moving forward, we have a lot of things we still want to explore. If we want to stay at the material level, I think if we want to predict failure, it's not only important to know the magnitude of these stress concentrations, but also the volume of material subjected to this elevated stress, because that's what's going to determine the ability of a crack to grow within the bony matrix. So although cracks may initiate in a really small region of highly stressed material, it probably won't propagate as far because it's going to quickly reach the boundary of the stress gradient. So there is a theory of critical distance that predicts material failure when stress reaches some critical value at some critical distance away from the stress concentration feature. So I think moving forward, the stress concentrations around these microarchitectural features that we determined from our finite element models could maybe be compared to some micro damage nucleation sites and crack propagation paths that we could explore using some contrast agents. I think it would be really cool to look at. And then if we want to move away from the material level and more towards sort of looking at these fractures at the whole bone level, I think some of the complexities of fatigue failure are really emphasized at the whole bone level, where these differences in structural geometry and density lead to really complex stress strain states. And there has been some existing literature that has found the articulating geometry of this joint can affect the likelihood of injury. So they found some aspects like the ratio of medial to lateral condylar width, or the sagittal ridge angle, or the width of the sagittal ridge have all reportedly contributed to fracture risk. So while there are several factors contributing to the development of these injuries, it's very likely that the stress the tissue is subjected to plays a really critical role. So these changes in joint geometry are likely influencing fracture risk by changing the stress distribution at the articular surface and any underlying subchondral bone. So to sort of explore that, statistical shape modeling is a really nice technique that can be used to quantify the average and principal modes of variation in shape, such as bone geometry. And then these modes can be, or these models can be altered by morphing the average shape along the principal modes of variation. And then if we combine these with some more computational models like finite element modeling or discrete element modeling, which is we've already done at this joint here, I think we can use these techniques to investigate how changes in joint geometry can alter the fracture risk at this joint. So I think if we are able to combine more of this whole bone modeling with some of our results from the material level, that'll lead to a really more comprehensive and nice multi-scale model of some of these injuries. So I think moving forward, that's something we definitely like to do. And I'd just like to thank our lab group and everyone else who was involved, as well as our funding sources.
So, floor is open for questions. Who would like to start? Philip.
Have some very basic questions. Are there, I mean, it's mostly related to your intro, I guess, for now. Are there differences in injury risk between the forelimbs and the hind limbs and these types of injuries?
So at this joint, they're more common in the forelimb. I don't think there's been there's a difference between left or right limb, but they're definitely more common in the forelimb and more so in the MC3 compared to the P1.
Okay. Then so kind of a follow-up question. I mean, you said left and right, but I assume that horses also have dominant limbs. Are there maybe differences in dominant versus non-dominant when it comes to these types of injuries?
So yeah, that's definitely something we thought about as well. So from what I understand, at least in the Japan Racing Association, a lot of the races do run both ways around the track. The horses will alternate which leg is leading. Maybe around the turn, they'll have one leg leading, and then when they push it straight away, they'll switch. So it doesn't seem like one is more so dominant, at least not like in humans.
Then I have a final question, which is a little bit more related to your data. You basically separated, I guess, the P1 and the M3, but have you also looked into potential differences between medial and the lateral samples that you took out?
Yeah, we're still kind of putting together a nicer statistical method to look at that, but really quickly, we didn't see any differences between medial and lateral in the MC3, but in the P1, there was a small.
So you had two types of bone, and I'm just wondering how do they differ and how they're loaded? And whether there's any expected correlation between the loading and what you see in the micro.
Yeah, so let's get back to the anatomy here. So with the loading, there's definitely contact between the third metacarpal and the P1. So really the P1 just gets loaded from contact with the third metacarpal. But I think with this third metacarpal, a lot of the injuries are generated from contact with the sesamoid bones. A lot of the injuries we see are more so towards the palmar aspect of this joint. So I think that's where we record our samples. I think that's one reason why we might have seen such differences in what these bones look like. Because even though they are articulating with one another, I was a little bit surprised why they look so different. But I think it's because the third metacarpal also contacts those sesamoid bones and sort of add some additional load to that.
Do you have any idea whether that could, I don't know, be consistent or be related to the skin depth?
Of the like thickness of the bone line fraction, I think it could be. I think, yeah, if it's being subjected to higher loads and stuff, I'd imagine there's probably going to be some more remodeling and in response to this training, this more adaptation going on there. So some other work has suggested on maybe a bigger subchondral plate and higher bone line fraction improves fatigue resistance. So maybe that's what we're seeing there.
Anyone else have a question? Yes.
Were you able to see a lot of sex or age differences?
That, I think we're still looking into that one, and a lot of those demographic parameters are still looking at into a little bit more. I think there was a small age effect. We especially had one older horse that was pretty weak. So still digging into that stuff.
I have a question. Andrew, is it so from the video I recall, it looks like the third metacarpal is predominantly loaded. Yeah, I guess like this image describes it well. So this bone is mostly going to experience axial compression in this case. Is it thought that the normal stress is mostly due to bending, or is it mostly
Sorry, for the
for
third
the
metacarpal.
and yeah, the third metacarpal? What's the predominant of the loading?
Yeah, I would imagine it could be probably a lot of axial loads for sure, I think. Especially because of this tendon running sort of more vertically, and that's just driving the sesamoid bones out into it.
And then you took the samples from this side and then here, kind of?
Yeah, from on the P1, we took them right from this surface, and then the MC3, we record them more from the palmar aspect here, more so where it contacts the sesamoid.
Yeah.
That's where we see more.
And
fractures.
with the P1 location, how did you decide where along the articulating surface is most of the stress at the distal locations near the tendons?
Of the P1.
Yeah.
So yeah, we cord from the articular surface. We're just hoping to get like a examine subchondral bone. And then based on sort of the size of our drill bit, we were a bit limited in terms of where we were able to get. So we ended up just flying one from each combine. I don't know if that's.
Are there visibly like just kind of visible differences in the bone microarchitecture quality between like the this distal portion of the phalanx versus the proximal like articulating surface
I know what you
phalanx?
mean.
That's what I mean. Yeah,
Oh,
like this
okay.
height there where I assume the majority of the stress is going to be loaded at this near the tendons, but I don't know if that's actually how.
Yeah, I'm trying to think. We did some like of our discrete element analysis. From what I remember, I think it was pretty well distributed across. The fractures do initiate sort of at this groove here. So maybe that's the region where it's even higher. But in terms of the sort of palmar and dorsal region, I'm not too sure about these arrangements.
And is it so with these morphological features, you have this, it's a smaller angle or is it a larger angle of this condylar groove that's associated with an increased risk of injury?
I don't remember for sure. I believe it was larger, but I would for sure have to go back and double check.
Anyone else have more questions? Walter?
Ask a couple of these questions. So when the horse just walks, then the fetlock point would not really be collapsing like we see in running, is that correct?
It extends, but definitely not to the same extent. Yeah, no.
So is it all passive structures or are there some muscles involved as well?
At this part of the distal end, there's no muscle. It's almost all just ligament.
So the deflection then would be directly proportional somehow to the amount of load that you get in the lower limb there. Because, you know, what strikes me, not knowing anything about horses, what strikes me, I didn't really think it was so bad for the bone. I was really more worried about that because I thought it would only be passive structures. I was really more worried about that. The ligaments around it and what might happen there. And would it be that when you get such large excursions in the joint that you might get inflammation of the ligaments, and that the inflammation might actually create an environment that's not good for the bone and might potentially affect the bone?
Could be, yeah, there's for sure a lot of injuries to the ligaments as well at this joint. There's like the superficial.
Injuries as well.
Yeah, absolutely.
Because the other thing, you know, you talk about overuse injuries, and at one point several years ago, I read what horses train, like horses that run a mile or a mile and a quarter, and compared to a 1,500 meter or 3,000 meter runner, you know, which would be equivalent distance for humans, they run very, very little. And I was really surprised about that. Like a human runner, a 1,500 meters, 3,000 meter runner trains many, many more kilometers and many more intervals than a horse. And so they run actually very little compared to humans in training. If that report that I read was correct. And so it's kind of surprising that it's that little running they factor, you know.
Yeah, maybe it's, I don't know, maybe it's an intensity thing. Maybe I think a lot of this industry is driven by a lot of money. And maybe if humans start to, I don't know, maybe they're just training these horses so intense that.
That's what they say. They train very intense. So they run 3 times a quarter mile or so at speed. But you know, for a human, that would be an absolute minimal training. You're not going to win anything at the Olympic Games if it's 3 times a week. You know, you run 3 times a quarter. It's just not enough. But a completely different question. You're in a running laboratory, and everybody talks about how do you prevent injury. And has anybody, I'm sure somebody has, so they will tell me, check out if it makes a difference on what surface these horses run, or has anybody thought about the construction of the horseshoe that might potentially prevent injuries?
There definitely has been, and we're looking at that at different surfaces, you know, moisture in the surface, the stiffness of the surface, you know, types of racing. We're looking at a lot of work focuses primarily on sort of flat racing. There's other work looking at barrel racing and different sports that they might play. So there have been differences. I can't recall exactly some of the surfaces they tested and what the results were, but yeah, there's definitely changes in fracture risk depending on the surface and the track and things like that.
Anybody looked at horseshoe design?
I think so. Also, from what I understand, I think horseshoes have been changed significantly in the last while. I think people have looked into it, but for the most part, I believe they haven't changed too much.
It seemed to be that the Fetlock joint was really big. You have that P1 horizontal. And you know, the horse is supported here is the hoof. That's the contact area. It's just one leg. what if you make the hoof a little bit beyond the end of the hoof and you got more concentration over that, you would shift that point of application, maybe a little bit more back rather than the front here, or I have no idea anything like that would work against. I mean, I've heard 30 years of body should be starting to the first thing that comes to mind.
Yeah, that'd be interesting.
All it's very, for example, in the UK, it's very tightly regulated. But people you're embracing. And
In what sense is it regulated like that?
in very dimensions and also protrusions and things like that, it's very tightly regulated. And the main concern that the trainers have is the weight of the shoes, so they all run with aluminum shoes. And they're very, very minimalistic.
So they have like, they are bracing.
Yeah.
bracing.
Flats.
Oh, yeah. Don't come up in the seminar.
What you always wanted to know.
Yeah, so we just had the Kentucky Derby, right? And 7 horses died leading up to that race, which I think was the most in a long time. Sorry? Oh, great. That's awesome. I want to know how many of those horses died from the Fetlock injury. Do you know
Yeah,
that?
I don't, I do remember something I had. And yeah, it was definitely more than they've experienced in the past. Yeah, I'm not sure.
Okay, if I find out, I'll let you know.
Okay.
The follow-up would be, so if I have. If I have a racehorse, can you help me predict, how do you translate this to the guy that has the money, that has the racehorse, and say your horse shouldn't go?
Yeah.
Right now.
Yeah, of course. I think that's the ultimate goal we want to get to. I think before we get there, what we're trying to focus on right now is just sort of developing more like a fundamental mechanistic understanding of what's causing these fractures. I think one thing we've shown is that you probably need imaging that can get down to like the micro level to look at some of these pores. Unfortunately, especially for horses, like the imaging modalities aren't there quite yet. So maybe this is could be a signal to maybe work on some of those areas. And then I think once imaging gets to that area, we might maybe at that point know what to look for in all this research. Right now, I think we need some of the imaging to catch up and go from there once we sort of get a better understanding before we start predicting.
Well, and it goes back to that they died training, right? They didn't die during the race.
Yeah, I think that's common, unfortunately, but there are like race day events too, but just as often during the training.
What happens to a horse that has the left picture injury?
The left, so they try to repair it. I think quite
How
some
do they
to humans with fractured plates and screws.
replace the screws?
Yeah, I think it's quite difficult to do. With a human, after you repair a leg or something, you can put them in a cast and tell them to rest for a little bit. As soon as a horse wakes up from surgery, we're putting 500 kilograms of weight onto that fractured plate. So that's what they currently do, but the outcomes still aren't as good as they are in humans for sure.
Can you suspense the animal? I mean, a harness and just lift the way off the earth is
Yeah, or yeah, possibly yeah. For I don't know for how long, maybe.
I'm not sure if they and
Yeah.
In there's ever eating or whatever.
Yeah, no, I'm not sure. Maybe.
Why, can you not get a horse to walk like a tripod if you can with dogs?
Yeah. One of the big problems that then they often develop injuries in the other one. The one that is not.
Yeah.
But you don't, yeah, it's interesting that you don't see that in dogs. You can cut off a limb of a dog, they learn to walk, and they could live, another 10, 11 years as a tripod. So I guess is this whole thing a selective breeding phenomenon? That we tried to create these horses that are so highly specialized and move fast that, we reduced the safety factor so much that it's inevitable.
Yeah, absolutely. I mean, I think that's not only that what humans have done, like horses have developed into working on one finger essentially. And I don't know from bones, but from the tendency safety factors are incredibly low in horses, so they're like 1.1, 1.2 or something like that. So it happens quite easily. And the more you specialize, the more you go into culverts and things there. I mean, the legs are heavy and gets worse and worse.
So the safety factors get smaller and smaller as you go closer to these high performing, but something like a workhorse is gonna have.
And that's a monotonic loading safety factor, right?
Yeah.
And so, this is cyclical loading, so it's gonna be lower.
Yeah.
So the horses that you use, were they race horses?
Some of them were, some of them weren't. We sort of got a variety of breeds and histories. We did have a few that were race horses, a few were total horses that have been retired for some time, but we did have a majority of them were previous race horses.
Differences between the race horses and other ones that were there differences in the microarchitecture that we saw?
I think we're still looking into some of those differences between breeds and ages and sex and things like that, but just trying to think back from some of the images. I think a lot of the race horses we have are also a lot younger. A lot of the older horses we have used to be race horses.
Just like technical, so we speculate that these horses have, how wide are they? How big are they?
On the app, so they're on the scale of less than 1 millimeter.
Oh, they're that big. So you're 24 microns boxing size and very, very easily identify all the for some reason I thought they were not smaller than that.
Pull up the photo.
Like here's all our tubercular development.
I think they're far less than 1 millimeter, but they're on the order of probably 100 to 300 microns.
34 microns, right? And the comment that you made, I thought that was really interesting. Like the horses that run one curve and the other curve that they changed lead day.
Yeah,
So first of all, what's the lead day at first touch? It's all the one that reaches out for like
the first touch,
the first touch.
I believe.
And so then you run.
No, that's second touch.
The lead day is the one that goes through the 3 seconds. And so intuitively, I would imagine that when you run a left-hand curve, you have a right lead day.
No.
No.
Left on that is.
Is that right? Left curve, left lead. And they do switch.
They do switch, yeah.
And they then run different around the curve.
But they can also run in the wrong one.
Yeah, but it's usually just, because it's not reason I thought that was a case, that force had a relay. In Dallas.
You know what else is really interesting with race horses, which I didn't know, is that when they get fatigued, like neuromuscular fatigue, not mechanical, when they get fatigued towards the end of the race or whatever, they increase their stride when they run, which is sort of the complete opposite of what you see when humans get fatigued, is they sort of tend to like
increase their cadence or slow down or whatever, but of course, these horses can't slow down. But they're not allowed to, but they actually, yeah, they increase their stride lengths. And some of the research that Tilo was showing me is saying that stride length, right, during a race is a very strong predictor of eminent fracture. Or eminent, or somebody that goes, a horse that goes on to get injured, right?
Yeah, there's some relationship with, they would reduce stride length by, I think, 10 centimeters on the street, that's very good.
Reduce, not increase.
Yeah, but it's right.
That is weird. Yeah. But yeah, they can kind of increase their stride length.
With this fatigue, they increase, right?
Yeah. How do you think the volume will go up to?
I'm not sure, what I'm worried about is the rolling time, I'm worried about that. Nobody else does that. And swimming, rowing, everything you look at, you know, people get fatigued and they decrease the shoulder.
Is that related to the breathing? Because they can only breathe when they're, when it's off ground?
Yeah, my speculation, so the horses, when horses galloping, the respiratory is really probably intimate with the stride frequency. So one inspection extra. So
I know that.
yeah, just increasing stride duration means increasing the inspiratory duration. Maybe.
So they can take a deeper breath that will take that off. Right. I was just talking about that a week or two ago about being trained breathing in animals in sports. And the horses as an example. Because they cannot do it differently. My understanding is that they gallop, people with the visceral movement. And therefore, there's some forward that the air is stretched out in the lungs. Because at one point, we're interested in breathing cross country skiing, which saves energy and actually dog it. And very. I also speak cross country skiing. I always say that I'm saying that it's like a galloping horse, eh? That's what I think about it. To me, cross country skiing, free state skating becomes galloping horse.
Yeah. Because the feeling thing, I don't know, like. To me, it's hard to accelerate and to skate. Is that true in galloping? The horses use another stance to accelerate. And once they have accelerated to the max or race velocity, do they then switch to galloping?
Or they think.
Yeah.
But I'm fascinated by that they're so easily able to switch their lead leg, because there's a certain coordination that might be case for one step to the other.
But it's also because one by one, so you can move on next right on the right.
They can do that.
Why would they do, when would they do that?
It's not, but they do that in the start at one of the. Fascinating.
We have any other questions for Andrew?
Questions.
I mean, they're all relevant. Okay, well, I'm gonna ask you a question since I have an interest. So you used stress volume for both these bones. That seems to make sense for the MC tree because you have generally, I would assume, pretty uniform density across the whole bone. Do you think strained volume would provide you with a better correlation for the first failings? What was the, I guess then there's two, but what's the rationale for using stress volume and why? And do you think it might differ if you use strained volume?
I think we like to look at stress concentration volume. Yes, just because we're trying to look at the stress concentrations arising from these, sort of these pores within the material. So last, it sort of makes sense that we're looking at stress concentration factors around some of these features to look at a stress concentration volume. And then if we want to look at strain volume, I'd be surprised if these have different results. I think maybe if we did, it would be more so in the P1 because they have more tremendous bone. Way advanced it's like just
We should do that actually. That's a good, because you do, he does. Because we changed the tissue. We changed the modulus of the tissue for the finite element model based on the experimental apparent modulus
From the CT scans.
from the chemical.
Oh, so it's a uniform.
So we apply a tissue modulus to the FEO
Yeah.
so that
That's
the
it,
parent
yeah.
modulus matches our experiment. So they are all getting a different tissue modulus. They like it would be a bit different.
Yeah.
Yeah, I don't know about the relationship, how much.
Well, presumably you can go from stress concentration volume to strain concentration volume, because all you're doing is saying these pores act as stress concentrators. And in those locations, then you just divide it by the modulus with the strain, right? Like all of the areas surrounding the pore, the farther you get, are gonna have large strain volume, right? Like if they have a high stress concentration volume, they have to have a strain volume there.
Yeah, well, I think the strain distribution will look very similar to the stress distribution. But why I think it might be interesting to look at a different threshold besides saying this is the stress of yield, and saying this is strain of yield. Is that we do every single horse has a different tissue modulus assigned to the finite element model. So if you assign a uniform tissue modulus, the stress is agnostic to whatever you assign the modulus, right? Yeah, and so it's going to be independent on what you assign to the tissue. But here is a case where we actually assign different tissue modulus based on the experimental results. So we should just see that changes.
So you change it based on the specimen, but then for even more to constant modulus.
Yes, because the apparent modulus, which you get from the mechanical test, is largely, it's more so determined by the effective cross-section area of the bone, the microarchitecture, and the tissue elements. But we essentially, it's a linear elastic finite element analysis. We do the analysis, we get the apparent modulus of the sample. We compare it to the apparent modulus from the experimental test. That gives us an idea of how we should change the tissue modulus to the finite element model so that they match. But the only assumption here is that there's no variation in tissue mineral density throughout the plane. The assumption is mineralized bone has one material property. But it can vary from point to point.
That kind of seems like a reasonable assumption to make in the third metacarpal. I guess like if I look at it, it seems pretty uniform, and then looking at the x-rays, it's like, yeah, it looks kind of uniform. But it seems more problematic from an assumption, or maybe not problematic, but it might be the responsible for the low correlations you're seeing.
Well, we do have an idea about that, but that's not NC3 versus P1.
Oh, no, this
That's
is different area.
Subcortical bone plate versus subchondral bone plate versus subchondral bone.
MC3 doesn't usually.
Yeah, so it's all just vertical, even in the diameter, in the ends.
For our sample. If the bone fraction decreases by the dimension.
Yeah. That's why it's just so, because it's just totally uniform, the bone plane fraction across there, so it's weird.
I was interested in that actually, go to the biggest effect.
Yeah, this guy here. So I can totally get PMC3 being more uniform, but where I struggle here is it's almost like it's more uniform, but it's got a lower bone volume fraction. And
Yeah, that, if you like the average between all the samples, they're almost like the same.
Yeah.
Even though they're so, they look so different.
And yeah, so I'm really struggling that these two curves don't start from the same point and then differentiate. And yeah, I have no idea why, but do you have any speculation?
To this extent, I don't know. I mean, we like cut the cartilage with like a precision saw, so like probably there's some of the cortical plate maybe gets nicked off a little bit just from like the sample prep procedures. I mean, I don't think I would have cut more of the subchondral plates, all the MC3s and all the P1s this like consistently. So yeah, why they especially start so differently. I don't know if I have any.
Could it be that because the plate is thicker, it doesn't have to be quite as dense?
Maybe, yeah.
Are there any other questions for Andrew?
I want to go back to the injuries and what I started reading up on the injuries. It says 73.58%. This is a fetlock. Were of the left forelimb.
Okay, so there was a.
So 3/4 of the injuries that resulted in euthanasia were in the front left limb. That would lead me to believe there is a dominant, I'm thinking about my cat, it's 4-legged, and I know cat's not a horse, but it's always using the right leg to. So I don't know.
The left holding,
The left
the
forelimb.
knee leg on left hand curve. And most of the time, I actually know that they're on right hand curves. I thought they always not left hand curve.
Different raising jurisdictions have different branches. But I think that will runs left, Hong Kong runs right.
Yeah, we're talking about North American horses. It's all left.
Another company is supposed to have just only the conduct localized. Okay, and they have Kevin Coke White, they posted and 3 conduit right? And again, one
So is the construction of the course different if you're on a left hand curve or a right hand curve? When you say, can you say you have 7 that are left handed or right handed, and then another ones that are, I mean, they would be exactly the same, wouldn't they? I mean, you just decide which way around you go.
but it might start case.
Yeah.
My data is from South Africa. And my iPhone.
We have to see 73.5 races are one day.
Yeah, so it talks about, and it also talks about, I'm sorry, I missed the name of the bones, the one that's on the end sesamoid.
Yeah.
That one's involved 55% of the time,
Those have a really high incidence of fracture as well.
at least in this cadaveric follow-up study.
Yeah, they for sure do. They're a little bit more difficult for us to like core samples out and test. They're super small. They break a lot of stuff.
So we have high capacity running rats. They're Fetlock rats. Very worried.
Okay, if that's everything for Andrew, let's thank our speaker again.